Just popped in.
Are you there, John?
The topic is a 630 meter operation, and our speaker will be John Langridge, KB5NJD, who is the MFLF column editor for CQ. So he has graciously agreed to Skype in this morning from locations, I say unknown. Mark, you know where he is.
Texas. Can you hear us, John?
Oh, Texas. Wayne is his.
There he is.
Good morning.
Good morning. Can you hear us?
Morning.
I can.
You want to introduce? Or did you already introduce?
We
introduced. I missed the introduction while we were going up. So you've been introduced
and hung up on.
and hung up on, and we have a crowd of about 60 people that are happy to see you.
Well, that's getting hung up on is the story of my life. But thank you very much for the opportunity to speak to you guys. Are we ready to do this now?
We're ready. Ken's in the front row and awake.
Okay, great. Well, thank you very much for the opportunity to speak with your group. Today I'm going to talk to you about something that has been a very big part of my amateur radio activity over the last 6 to 10 years, and that's the 630 meter band. 630 meters as well as 2200 meters were granted to the amateur community last year. First amateurs on the band were October 13th, 2017. And been a lot of activity on the band. Much of that activity has been very different from what people they'll be surprised about what I tell them about what's been going on. It's not what a lot of people have expected. Now, full disclaimer here is you're going to leave here today with more questions than answers, more likely. This is an hour-long talk, and we're only going to scratch the surface. The reality is you could turn this content into a semester-long university course with all of the ancillary competencies that one might have, or one might need. What I'm going to discuss with you today are mostly practical applications, okay? And I'm going to focus in on a few things that I think are very, very important. If I leave something out or if I skim over something, it doesn't mean it's not important. It's just the reality of these short talks. So you will probably have to rely on a number of external references. For example, a number of those are web references. I highly recommend people look at the links page on my website. If you go through those links and those sites, you're going to have all of the information that you need to effectively get a station on the air. It's important, I think, that you see what other operators are doing and see a lot of the technical portions of actually getting a station on the air. And I will provide Mark a link, or a set of links, I guess, after this talk is done so that he can put them on your W5NOR website. So as an overview today, we're going to talk mostly, we're going to start out today giving you an overview of what's gone on 630 meters over the course of the last year. I'm going to focus in, at that point, on transmit antennas. This seems to be a topic that a lot of people have problems with and a lot of people get hung up on. I'm going to focus in on one specific approach to antennas and give you a couple of means of resonating and matching those. I'm then going to finish up with a discussion of radiated power and how to apply that in your own station and my thoughts on the process overall. Now, there are a number of ways to handle what we're going to talk about today. This is just, what I'm going to tell you about today is just my approach to it. There are a number of other individuals that have other ways of doing it. So that's one of the reasons that I think it's important that you look at the links and see what other people are doing. I think having a good understanding of what people are utilizing on the air, I think will be important to your success on the air as well. So without further ado, I'm going to go ahead and share my screen here, and we're going to get into the presentation itself. Let me know when you see.
We see you in front of your spreadsheet or your presentation.
Okay, so you're seeing a presentation.
Beautiful. There you go.
Okay.
You can take my ugly
there
picture
you
off of there. Yeah, there you go.
Okay, very good. Okay, so, let's see, I just clicked on this. Let's see if it moved on. Okay, so I've given a lot of talks on this topic since 2012. That was when I started really getting really active in this particular niche of amateur radio. So I've had a lot of opportunities to talk to a lot of different people about their thoughts on this. So the people come into this with a lot of preconceived notions. Many of them will say that you really can't do anything with 7 kilohertz or 5 watts of radiated power can't be heard. Natural and man-made noise is certainly a concern, but we've dealt with that for a long time on 80 and 160 meters. I can assure you that it is possible to erect an effective antenna on a normal suburban lot. In fact, we have 2 individuals, one that's operating from an apartment in San Francisco and effectively being heard and making 2-way QSOs, and one that's living that's living in a condo in Ohio, and he's, last count, he had worked 10 states. So you can do amazing things. And of course, there's the idea that no amateur equipment transmits on 630 meters. That's part of the problem of the manufacturers themselves. They haven't done a very good job talking about that in their literature and information. So you really have to embark on this with, you have to suspend your disbelief, because all of these things on this page are not true. So, where is 630 meters? Well, it's really this chunk of band below the AM broadcast band. And the reason I point this out is that I've actually had people say, well, 472 to 479, that's somewhere above the 70 centimeter band, you know, and they're not thinking in terms of the units associated with those numbers. But here we're definitely talking about the AM broadcast band. We have navigation beacons down here. At the lower end, of course, 2,200 meters is down here, WWVB on 60 kilohertz, and a few navigation beacons between the broadcast band and the 630 meter band. Now, this is kind of the layout for how the band is been utilized so far. Primarily, CW is used below 475. That's generally where most of it remains. Digital activity has remained between about 475, 0.6, 0.7, up to around 476. And that's generally been the JT modes. And we'll talk about that a little further, just a few moments. Wideband modes have widely not been tested at this time. We do have a few guys that have made phone contact with considerable difficulty, and these were individuals using rather large stations. So the average person is going to have a hard time probably making phone contacts if they're utilizing legal power. I do have a breakdown on my website, which we'll look at here in just a bit. On my website, it's actually the link is on the front page where it talks about a band plan, and it does a breakdown for all the various modes that are in use. So, season 1 ended on August 31st of 2018, and we had 115 operators that made at least one 2-way QSO during the course of that almost a year. 3,500 2-way QSOs is quite a few. But we had a number of guys that were active every night, working, in some cases, the same stations, turning it into a competition to see who could work the number of stations through the summer, the highest through the year. Our seasons typically go from September 1st of one year to August 31st of the next year. And we have filled in some holes in this map since the new season started September 1st. the fight for WAS has been a fierce battle, and it's one that continues to go on. Currently, NO3M is at the top of the list. I think last I heard he was at 38 or 39 states confirmed. So it is certainly possible to make contacts on this band. There also have been a number of DX contacts that have been accomplished, both with Europe as well as Oceania. In fact, just yesterday, Rob Sherwood, NC0B, completed a two-way QSO with Roger Croft's VK4YB in Brisbane, Australia, during sunrise. During sunrise in Colorado, and that actually is a new world record, as a matter of fact. So for two-way QSOs. So what modes are typically in use? We typically see CW and digital modes. Digital modes certainly popular, JT9 and Whisper. WSQ coll is a relatively new program that it's a keyboard-to-keyboard type QSO mode that was developed by Murray ZL1 BPU and Kahn ZL2 AFP. Candidly, I think that the interface, the user interface, is a bit clunky, and there are a few bugs, but they're working through those. And I think in the future there may be some real options. But there are some FSK-based modes like Domino EX if you're a digital mode operator that work well with non-linear amplifiers, which are very common. Of course, JT9 is really been the go-to mode for digital mode two-way QSOs. You may notice that you don't see any FT8 listed, and part of the problem with FT8 is that with the reduced speed between the cycles, you end up losing a lot of the noise handling capability and depth of decode. And so we don't really see FT8 as a big player on this band so far. Quite a bit of CW, and I'm mostly a CW operator. I do work a bit of JT9 as well from time to time, but I am primarily interested in CW, and a lot of these guys are the same. We enjoy getting on and rag chewing. Very little phone, oddly enough, and as I indicated, running legal power over most paths. Most people are going to find it's a bit of a challenge. It is a weak signal band, so that certainly figures into it, and it does require a linear RF chain. As I mentioned, much of what we're utilizing on this band is non-linear amplification. So if you do have interest in working sideband, I would encourage you to locate that on either 476 upper sideband or 478.8 lower sideband, and that'll keep you as far away as possible from the weak signal modes that may incur some interference from that. So propagation on 630 meters is, in many respects, it kind of looks like 160 meters, but on steroids. Now, during daytime, we get a lot of primary propagation mode is ground wave, and we see some sky wave during the winter. In fact, I've made daytime QSOs with NO3M during January at noon over roughly 1,700 kilometer path. Now, 200-mile ground wave is really easy for two well-equipped stations, or multiple well-equipped stations. I think that there probably is an MCOM application here. I did write about that or give some thoughts on that in my October 2018 CQ column. But I think that there's a lot of work that remains with propagation in terms of understanding it. If we thought we didn't know much about HF, we really don't know much at these frequencies. Nighttime is a skywave band. We see a lot of E layer propagation, and long haul openings, DX openings, we believe are probably in some way affiliated with E and F layer ducts in much the same way that you see on 160 meters. It's pretty well established through ray tracing studies that on 160 meters you see on the order of 10 dB of loss per hop on long haul paths. So that would effectively render some of these long haul and typical paths to be impossible to achieve. However, we see similar situations on 630 meters, and more than likely, the losses that we're observing are even higher than that 10 dB figure for 160 meters. So for weak signal operators, it is very possible, and I do, whether I live long enough to experience it or not, I do expect that that there will be a day when DXCC will be achieved on 630 meters, as crazy as that might sound. And here's just a diagram showing the various propagation regimes. On 630 meters, we see a tremendous amount of daytime absorption with the D layer during much of the year. This is why we are able to observe the ground wave at the level that we do. Don't believe that there is much in the way of NVIS, but that has not been thoroughly examined at this point. At night, again, we see skywave, which is typically the E layer, sometimes with intervention between the E and F layer on those duct modes. So, where do you start? Well, probably the best place for you to begin as a person that's really interested in what we're doing here is to know what the specific rules are for operating on 630 meters. And these also go for 2200 meters as well. But they are very unique to both of these bands, and that is that our antenna structures are limited to a height of 197 foot, which is roughly 60 meters. Now, you may say, okay, that's not a problem, but we actually have individuals that have antennas that are operating at around 197 foot. Frank Donovan, W3LPL, is running an inverted L hanging off of his 197 foot tower that supports his 160 meter four-square array. And it sits over about 25,000 feet of radials. And it's 197 feet tall and about 300 feet of top loading configured as an inverted L. It only takes Frank between 6 and 10 watts to accomplish 5 watts effective isotropic radiated power on these bands, which is our next limitation, 5 watts EIRP. And that has to be generated with no more than 500 watts total power from the amplifier. And we'll talk a little bit more about what all that means here at the end of the discussion. You are limited to fixed stations. Okay, now that also includes fixed portables. So if you have a field day site, if you have an EOC, those are certainly fair game, provided that you meet the final requirement, which is notifying the Utilities Telecom Council or Technology Council 30 days prior to beginning your operation. Now, the Utilities Technology Council is sort of a lobby organization. They're a political organization that coordinates frequencies for power line control systems, PLC systems, that are used to control and monitor activity on transmission lines. We're specifically talking about transmission systems, not distribution systems. Normally at this time, I go through the process of registering or notifying, sending a notification to them for a specific site, but in talking to Mark, it sounds like he's been working with a number of individuals to accomplish that. So really, I won't go through that process today, but I will give you one tip when you are submitting that notification. You will have an option to select bands for 137 kilohertz or 472 to 479. I would encourage you to send notification for both of those bands. That's the reason. If at any time they make the decision that they are going to tell you that they raise an objection, or if they're going to raise an objection with you about operating on those bands, they're not going to tell you which band they're raising the objection for. They're just going to say, sorry, you're not, we have a problem with that, and they'll send you a notification, and that'll be the end of it. By doing it individually, you'll at least have an idea of which band that they're talking about. One of the reasons that it's important to submit this notification has less to do with any real interference with PLC systems, particularly in the lower 48, where it's not a real issue on 630 meters. But it prohibits UTC from coordinating PLC systems within a kilometer of your station in the future. And so this is not a real issue, but it certainly takes that takes that possibility off the table in the future.
John, has anybody been turned down?
Not on 630 meters. Occasionally you'll hear people claim that they have been rejected, but when you dig a little deeper, you find that they were rejected because of clerical errors either on their end or at UTC's end. There have been a few people rejected on 2200 meters. What we're finding is that that's because there are, once again, clerical errors and data that wasn't removed after the PLC systems transitioned to a new technology. Okay, so going forward, talk a little bit about receiving. This is, I think, a really good place to start for people. If you can't hear, it's not really worth anything, and it may require you to do a few things at your station or in your area to help improve your receiving conditions. Most people who have HF rigs typically begin with their general coverage receiver. I can tell you straight up, this is probably the worst approach to listening on the bands for the very first time. Most general coverage receivers have attenuators for the broadcast band that are not removed whenever you exit the broadcast band. And frankly, the sensitivity is not very good, but it certainly is an option for a lot of people. Receive-up converters are certainly another option, and pictured here is the Jackson Harbor Press receive converter. And what it does is take signals in the 472 to 479 band, or really anywhere below the broadcast band where the filters will allow a signal, and it converts it to a frequency that is maybe better suited for your HF rig, maybe 80 meters or 10 megahertz, where your receiver has better sensitivity, better quality, better filters, and overall better functionality. The nice thing about the Jackson Harbor Press board is that it's about 20 bucks shipped, and I do have a link on the links page for that. It's not a bad way to get started. It is a kit, and it tends to be a little hot, so you may need a little bit of a pad off the end of it to bring the levels down a little bit. Modern transceivers are also a very good option. The K3S, the Elecraft K3S, is certainly has a very good receiver with the options built into it. Certainly an upgraded K3 works very well. Newer Kenwoods, the Kenwood 590 and the 890 also have very good facilities because they're designed to receive at these frequencies, and that works very well. SDRs, modern SDRs today are very, very good options. Many of them do a very good job, like the Soft Rock Ensemble 2 LF. That is a very good, very inexpensive approach. I don't know if those are actually on the market anymore, but if you can find one, they work very well. I would also comment that I think the Flex, a lot of those radios, particularly the newer ones that have upgraded low-pass filters, will work very well also. Next step, you might want to generate a signal and maybe get your station on the air. And as I mentioned with the receive, many modern transceivers also have drive level output. So what that essentially means is they have 1 milliwatt out that's designed to be amplified by a larger outboard amplifier. This is very common. In many respects, this is a very, very useful approach for guys looking to operate digital modes. And I often recommend using an amplifier like K5NL's digital mode amplifier, Class-D amplifier, or a comparable design. And we'll talk more about Ken's amp here in just a moment. As I mentioned with receive, a number of SDRs also generate a low-level signal. I think the Flex will also do it. I think the ELAD Duo will also do it, as well as a number of others that are currently on the market. Another option is a transmit down converter. One that I'll talk about a bit more in a moment is the MF Solutions converter. Like the receive converter, it really does the opposite. It'll take a signal from an HF band that your transceiver will work at, maybe 80 meters or 30 meters, and mix that with a local oscillator, filtering the addition product and leaving the difference product, and amplifying that, and giving you a usable signal that works very well on the band. CW, this is how I generate CW with a GW3 UEP amp. It's a waveform shaped Class-D amplifier. I do that to avoid key clicks. There is some information on the front page of my website down at the bottom that will give you some details about that. I used to build those amps for people, but it's become too problematic, so I don't do that anymore. And of course, transverters are a big player now. The monitor sensors transverter and the mini kit transverter. Both of these we'll talk a little bit more in just a moment. These are both out of Australia, and they do work very, very well. But there are some caveats about the mini kits that I'll talk about in just a moment. The main thing you really want to avoid is wideband transceiver mods for your transceiver. A lot of transceivers, ICOMs were really big about this. They had the Mars and Cap mod. Back in the day, and people would clip a diode or clip a resistor and would open it up for transmit anywhere. That's okay for bands near amateur bands, but when you're talking about down at the bottom, down below the AM broadcast band, you're really utilizing that system really out of spec, and a lot of guys have damaged transceivers and had all sorts of problems going forward because of trying to get too much power out of those transceivers. Now, it is kind of a false economy as well, because individuals will see on their power meter that, hey, I'm getting 40 watts, I'm getting 50 watts out of this thing, and it says 472. Well, in reality, what you're really seeing is an unfiltered harmonic-rich signal, and you're probably seeing about a watt at 472 and 40 or 50 watts, the balance of that being harmonic content. And contrary to popular belief, the antenna system Q will not amply filter the antenna, or filter that rig. You do need a low-pass filter if you're going to go that approach. If you do choose to go that, I recommend you running the power way down and driving an external amplifier. But again, I really can't recommend that, and there's quite a bit of information on my instructional page about that as well. Now, K5NL Class-D digital amplifier. This is what I use for JT9 and digital modes, nonlinear digital modes. Ken did a great job with this amplifier. As far as I'm concerned, it's pretty bulletproof. It has facilities in place for a receive signal pass-through, so that you can drive the signal from your transmit antenna, if you wish to receive that way, back into your transceiver. It operates at about 93% efficiency, and remarkably, it'll take drive level on 472 in spite of the fact that it is operating in that push-pull configuration, which oftentimes requires you to multiply the frequency times 2. Ken has worked around that and come up with a really nice system. This particular design will generate about 100 watts, which is pretty darn close to what most people, the average ham, will need to generate the 5-watt EIRP signal at these frequencies. And we'll talk a little bit more about that when we move forward. I'm a big fan of Ken's product here. It does work very well, and it has been very reliable in my station for use with digital modes. Now, John Molner's MS Solutions transmit converter. John is up in Vermont. This is kind of what it looks like. It's a kit. It'll generate about 22 to 25 watts out, and at 630 meters. Uses an onboard local oscillator. It also has an outboard port for a GPS disciplined oscillator. And John will build these for a fee, build and test. But I do have information on the front page of my website about this. One thing I didn't mention about this, as well as Ken's amplifier, matched loads are really, really important when you're using these Class-D and Class-E amplifiers. They don't tend to like reactive loads, and so it is important to maintain a matched system on those. And we'll talk about that a bit more when we get into antennas. Now, If you do have questions about your ability to match and resonate your system, the monitor sensors transverter may be the way to go. And it really is kind of the Cadillac in that Roger Croft's VK4YB has built in a lot of safety features into this, which really makes it virtually impossible to destroy. Eric Chansky, I think, reviewed this, NO3M reviewed this back in June or July, I think, in QST. He did everything he could to break one down, and he couldn't do it. So basically, it uses 160 meter IF. It is a linear PA, so you could use this for phone or linear digital modes like PSK31. In my opinion, the receive section on this is excellent. I own a couple of these, and it makes my FT1000 sound like a K3S, and I absolutely love the receive section in this particular system. It does do 50 watts out, and it will do that continuous. The drawback, if you call it a drawback, it is shipped out of Australia. It is pricey, and there is a shipping fee associated with freight that is somewhat considerable. But I do have information about this as well as a manual on the front page of my website. The next kit option is the MiniKit's 630 meter transverter. It is a kit. It is out of Australia, minikits.com.au. I think it's running about $110 Australian plus shipping, and I think the shipping on that's actually pretty cheap because it's in a padded pack. But at any rate, you do see a lot of through-hole components. I would caution you, though, that the other side of this board has a significant number of surface mount components. So if you're not skilled at doing surface mount soldering, this probably isn't the route for you. But there is a lot of support for this and an active community online for this particular product. Now, how are we doing on time?
10:49, we're good. You got
Okay,
40
very
minutes.
good.
40 minutes, you're good.
Excellent, thank you so much. Okay, so antennas. I'm gonna only mention receive antennas at the moment. That's really its own discussion in and of its own, in and of itself. There are really two types of directional antennas, or really two types of antennas. There are directional antennas and non-directional antennas. Really successful, a lot of very successful stations improve their signal to noise ratio, which really is the name of the game in this discipline, using directional antennas, or some type of receive antenna. 160 meter operators may be familiar with the K9AY loops. Those are certainly very functional receive antennas at these frequencies. And another thing about them is that they are quite scalable. So you can make them larger to if you feel like you need a bit more signal. You may have to adjust the termination resistance so that you get maximum null off the back of the antenna. Also very popular today are multi-element short vertical arrays, active vertical arrays like the high Z vertical array. That's become very popular. A lot of the DX engineering arrays are also very good and very popular. And even with relatively close spacings, they can be good performers provided that if you're using the active antenna approach, you match the amplitude on every one of those small preamps located at the antennas, and you're careful in cutting your phasing and delay lines. I hear a lot of people that are pretty sloppy with that, and the results are that they get poor performance. But receive antennas are really kind of an important part of listening at these frequencies, and it would be a shame to put a high performance receiver out there just listening to noise, because there really is a much bigger world out there down at and below the noise floor. So where I want to focus today is on transmit antennas, and I can already tell you I'm going to focus on the monopole vertical, but I did want to mention the vertically oriented loop and the dipole, because they are players from time to time in this 630 meter game. First season on 630 meters, about 99% of the stations that were making two-way QSOs were using the monopole vertical. We had less than 1% of those users were using vertically oriented loops, and a very small number were using half-wave dipoles. So I want to talk briefly, very briefly, about the vertically oriented loop, and I really hadn't intended on saying much, but given that N1VF Ben has had a tremendous amount of success operating with a loop from his apartment, I think it's probably worth making a few comments on the topic. Vertically oriented loops are somewhat different than what most people are used to. If you've ever used a cloud warmer on 160 meters or 40 meters, maybe for talking to a local group, they're typically horizontally oriented and oftentimes a wavelength, maybe fed with ladder line or a balun or some type of transformer to match the impedance. Well, this is a little bit of a different situation. Imagine if you took that horizontal loop and turned it 90 degrees so that you had a horizontal wire, two horizontal wires and two vertical wires. You know, supported by a tree, supported by some type of support that you had available to you, and resonated that with a capacitor in series with each end of the loop. That's really what we're talking about here. We're talking about loops that are a fraction of a wavelength long. In the case of the loop used by N1VF at his apartment, he pulled high voltage wire through a tree adjacent to his balcony and resonated with a vacuum capacitor and applied power via transformer coupling. The antenna was really intended to be a full wave loop on 40 meters, and he's been heard at my station here in Dallas transmitting JT9. He's worked QSOs with KL7L up in Alaska. He's heard in Hawaii by K9FD and out in Hawaii, and all other manner of stations up and down the West Coast. It actually happens to be oriented north and south, which is really the direction you typically see in that configuration. Often, when you're dealing with these short loops, you're dealing with radiation pattern that is often in the plane of the antenna rather than through the antenna itself. And so it has a bit of a figure eight pattern that's somewhat distorted. But anyway, that's your vertical, that's your information on vertical loops. I don't particularly like to use them that much myself. They do tend to work well in situations where you have a cluttered environment. So you've got lots of trees, lots of poles, maybe you have light poles or power poles. And the reason for that is that they're magnetically dominant. So in the near field, I should say. That doesn't mean that they won't experience losses associated with ground and attenuation going through trees and other living tissue, but they do tend to work well for people who use them in those environments. They have very low radiation resistance, and they tend to also have a lot of high angle components, so that may or may not be useful to you. The other antenna that a lot of people utilize, or say a lot of people, a few people utilize, is the half-wave dipole. And that may sound crazy, but there are people that have 1,000 feet of horizontal space available. And a support that is often too low. Actually, really any support that's available to amateurs is going to be too low for 630 meters. But individuals try to do it nonetheless. Again, you're getting a situation where you have a very low radiation resistance, you have lots of cancellation of signal because of the ground effect. I don't recommend this approach. For even if you had 197 foot tower available to you, I'd tell you make a vertical. If you had a 50 foot tower, I'd tell you to put up a 30 foot vertical or a 50 foot vertical and go with that. really, your effectiveness using a dipole is going to depend on the ground conditions under you. Oftentimes we see dipoles working very well at low frequencies for long-haul communications near the equator or near areas where ground conditions are very poor. I think you guys are very similar situation to what I'm in, and I have very good ground conditions, very good average ground conditions. And so it makes it a very good good place for a vertical and not so good of a place for a dipole. One anecdote that I can offer about dipoles, there's an individual that is located in the southeastern U.S. that he was pretty adamant about using a dipole because he was so concerned about the ground losses that he might incur with a vertical. But the reality was, I've never heard him on the air, but I hear the guys in his area that are running the 43-foot verticals that are top-loaded and base-loaded against an effective radial system. So there's your anecdote. I think that's something that's really important to keep in mind. If you've got a lot of space and you wanted to try a dipole, I mean, it's going to cost you 1,000 feet of wire. Okay, so you can always cut that up and turn it into radials later whenever you find you're dissatisfied with that approach. So, monopole vertical is where I want to focus all of my attention on antennas today at this point. There are a few priorities that we like to look at with verticals, and that's as tall as, we wanted a vertical that's as tall as possible. Doing so will maximize your radiation resistance and force current higher into the antenna, of course. Capacitive top loading is certainly very useful. This is typically in the form of top loading wires. We oftentimes consider capacitive top loading to be the only really quote-unquote lossless loading method, aside from ground losses incurred under the antenna as well as or under the top loading wires, as well as resistive losses in the wire itself. We like to see a high Q loading coil. Okay, typically fatter coils are preferred. Don't be like one guy that he was intent on using a 6-foot tall, 1-inch piece of PVC to wind his coil on, and that didn't work out too well for him. Certainly very low Q and really problematic for him. Radial system is, of course, a very, very important piece of the puzzle, particularly near the feed point. If you told me that you had 500 feet of radial wire available to you, I would not tell you to put 5 100-feet radials out. I would tell you to cut those probably into 20-foot sections and really fill in the holes around the feed point. That's where your maximum current density is going to be and where your highest losses are potentially going to be. I've used large diameter conductors. You know, a lot of us have at one time or another used a wire vertical. I think wire verticals work okay, but they're going to be subject to a lot of variability whenever the weather changes, whenever the seasons change. That's going to be a major player. You're going to see a lot of instability in the wind as well. Going to a larger diameter material, I think Ken uses, 4-inch irrigation line. That's a very good selection. I use DX Engineering telescoping tubing. I think it's about 3 inches at the base and telescopes upward to about 80 feet. And that approach works very well for me. And of course, high quality insulators, whether that be at the base or whether that be at the ends of your top loading wires. And we'll talk about why that is so important in just a minute. Now, there are a couple of classes of vertical antenna that we deal with, or rather, a couple of ways I should say that we load and match those antennas. And the way that the approach that I like the most is the Variometer fixed coil loading method with some type of matching, whether it be a transformer, whether it be some other network. In this particular case, you can see You've got a fixed coil in series with a movable coil, the variometer, in series with the vertical element, and there is some degree of top loading, whether that be some type of T-top wires, bicycle spokes, umbrella wires. We'll talk about those a bit more in a bit. And of course, we use some system to match those, that to the coax, because you're often dealing, they're pretty variable feed point impedance on these systems. Of course, radiation resistance for any antenna that we're going to use is pretty low. In general, you probably aren't going to see higher than 1 to 2 ohms of radiation resistance. And it's often very common to see between half and 0.6 of an ohm of radiation resistance. The rest of that feed point impedance is loss resistance. It's well, that includes ground losses, environmental losses, conductor losses, loading losses, things like that. So it is conceivable that with high enough losses, an individual could have a 50 ohm match without any type of matching network. I don't, however, recommend that approach. I recommend adding more radials so that you are forced into the situation of using a network. Now, many of us that use this variometer approach utilize a means of both remotely resonating and remotely matching the antenna. There's a reason for that. Actually, I'm getting a bit ahead of myself here. Let me back up and say that we as we do have a means of matching the antenna and resonating from the ground, the reason we have to do that is that we like base-loaded verticals. And we would never tell anybody on HF to put a coil at the base. If you'd probably tell them to put it somewhere in the middle or somewhere at the top, or not use a coil at all, instead using capacitive top loading at the top in lieu of that. The reason that we like base-loaded coils is number one, we're regulated by radiated power rules. So any losses that we incur by base loading, we can simply make those up with power. Now, again, we never tell someone to do that at HF. At HF, we have a different situation. We're allowed to run 1500 watts PEP on all 10 to 160 with the exclusion of 60 meters. Of course, 60 meters is kind of in a similar boat as 630, being a radiated power regulated band. So we don't worry so much about the losses associated with the antenna, and we locate the coil at the base. It creates a more mechanically stable system. And oftentimes we find guys that will try to put coils up high, and they'll have inclement weather. Maybe they have an ice storm, and sure enough, they'll have a flashover on that coil, and they're having to pull the vertical down or remain off air until such time that that the weather is good enough to pull the antenna down to work on it. That happened to Larry Molitor, W7IUV, up in the desert of up in Washington, and he finally went to a base coil that he could resonate and match dynamically, which has really saved him a lot of grief in terms of maintenance. A lot of these verticals we're using are very tall, and so the consequence of that is that they become very mechanically unstable. So trying to add a coil up high really can be problematic. So this is one of the reasons that we utilize the base coil, and having the ability to remotely both resonate and match the antenna gives us the ability to maximize our antenna current. And that's where the rubber meets the road for transmit antennas, is maximizing your antenna current within the legal confines of operating on the band. So that's why we choose to use okay, so here's a variometer. Here's one that John Molnar, WA3ETD, has pictured. John really wrote the book on these bucket style variometers. What I like about the bucket approach to variometers is that you can go down to Home Depot and get everything you need. You don't have to worry about you know, a lot of other items to get yourself running and on the air. John wrote a really good construction article in the September 2017 issue of CQ magazine with all of the instructions, and he also has links on his website, which I'll show you here in just a bit. That has basically all of the same construction information. But here you see, what you see here is the fixed coils with taps on one side and a grounding wire hanging off the end. Inside of the bucket you have a movable coil, and this is actually the variometer that I utilize at my station. It's actually rotated by an external motor. It's an Archer antenna rotator that's external to this to the ATU tub here. Mounted 90 degrees, and I only have to turn the thing over 90 degrees to match anywhere within the band. Your number of turns on this inner coil, typically 15 turns per side is what I'm utilizing. That allows me to get anywhere in the band. If you were to reduce that number, you might potentially reduce your flexibility and where you could resonate within the band. Now, what I do like about this approach is that it makes it very easy to select the tap that will ultimately work best for you. It makes it very good for portable operations as well. Probably one of the detriments of variometers is that they tend to be somewhat inherently lossy compared to some other methods. But again, we don't really worry too much about those losses because we can make those losses up with power. Now, the next approach that I want to talk to you about is very similar. It's the series LC method using a shunt match. This is the same approach that Ken K5NJD uses. He has a combination of base loading via a series LC network. You essentially have a fixed coil that has more inductance than is necessary to resonate on the band in series with a variable capacitor, and you want it to be a high voltage capacitor. He uses a vacuum variable to accomplish that, and he also uses a motor drive via stepper motors to move anywhere within the band. And that combination, utilizing top loading wires, has worked very well for him. Now, he also uses, in the pursuit of matching the antenna, he uses a roller inductor. It's a shunt coil to ground, and he essentially taps onto that coil, that moving coil, to determine his match to 50 ohms. This is a very good approach, and it works very well. It works very well for Ken, certainly. It does not give you the opportunity to have a DC ground path, so I do recommend some type of lightning horn on the antenna to allow lightning to jump to ground. That can certainly save you a lot of grief as well. So that same approach that Ken is using, here's a somewhat close-up image of NO3M's implementation of that. Here you see a coil mounted on top, feeding the base of this vertical. I think he uses a 68-foot vertical. The coil's in series with this vacuum variable driven with a stepper motor. And he uses a shunt coil here in this particular image to ground his radial system that's also driven by a stepper motor. Now, like Frank Donovan, Eric's system is located in the middle of his 160-meter foursquare. So he's sitting on about 20,000 feet of radials in the middle of that antenna, and utilizing a bicycle spoke top loading on this particular system. I'll detail a bit later. Eric has actually gotten away from the roller inductor and gone to a ferrite transformer, broadband transformer. And the reason for that is that he found that he had reliability problems with the contacts on the roller inductor. More of an environmental issue. It's really hard to keep moisture out, and a lot of the tarnish and whatnot that occurs on these silver platings really drove him away from that. So there are a number of top-loading schemes. The top load, the T-top, the classical Marconi T, as we like to call them. The bicycle spoke, multiple wires at the top. Oftentimes, you see the multi-wire approaches. You like to do a skirt wire because it will significantly increase the capacitance. You also have the umbrella wire approach, which would also benefit from a skirt. A lot of people, there are a lot of different opinions, I should say, of how far the skirt wire should decrease into the field of the vertical. Some people say no closer than 50% of the vertical. I think W8JI's approach was no further down than a third of the top of the vertical. So your mileage may vary on that. What you want to avoid is out-of-phase currents that will effectively negate your field strength. Another approach that is often used is the classic inverted L. A lot of times you will see a lot of high-angle radiation from this approach, but it is a very convenient means if you only have one tall support available. Now, I mentioned earlier that I like practical application of a lot of these ideas. And in many respects, it's very simple to take an HF dipole that's hanging in quote-unquote free space and utilize it as a Marconi T antenna. Now, it's important to stress that word free space, and we'll talk in just a few moments why that's important. Voltages are certainly very high on these antennas, and so you can start fires very easily. I have a page on my website that's known as the Hall of Flame, and it details a number of images showing fires that have been started by antenna systems. I seriously encourage you to take a look at that. And truthfully, I'll also add this bit of information. A lot of things that guys do at HF will get them killed if they do the same thing at 630 meters. The currents and voltages associated will create all sorts of problems. So you really have to embark on this in much the same way that you might if you were working on an amplifier. Okay, so dipole is a T antenna. Well, you've got a feed line here, which actually acts as the vertical component, and the leads of the dipole actually function as the top loading. You can use a number of configurations where the feed line is close to the support, provided that you don't. It's a insulated support. You'd have a coil at the base of the antenna, and then basically resonate the thing with respect to a ground system. This is very doable, but there are some important caveats to that, and that is that if you're supporting it from a tower, this is really how you need to support the thing. You don't want the feed line coming back to the tower and coming down the center of the tower as you might in a properly installed coaxial system where lighting protection were your goal. Again, this is the vertical radiator, and so it is going to have a lot of high voltage on it. And I promise you, no degree of coaxial shielding is going to be enough to insulate the high voltage that you're going to encounter on the system. So you do want to use some type of yard arm that's insulated to support this particular configuration. Now, mentioned high voltages are very real. Well, high voltages scale with the capacitance, or excuse me, the capacitive reactance of the system. So for a given amount of current, the shorter the antenna is going to mean a larger capacitive reactance, which is going to mean a larger voltage. And this is just one representation of how that plays. So let's look at a specific example. This is a specific model that NO3M had in his presentation. In his particular example was a 30-foot high, 40-meter dipole configured as a Marconi T vertical. Okay, so you're talking about 33-foot legs. His model shows about 2.227 ohms of radiation resistance and about 1954 ohms of capacitive reactance. When you plug that number in to the formula, assuming 5 watts EIRP, which also breaks down to 1.67 watts of radiated power, you end up with 5.3 kV on that antenna. Now, there's nothing inherently wrong with having that high voltage there, but you just have to be able to handle it so that you don't create a hazard, whether that be for fire or for life in general. Another approach might be an 80-meter antenna. And here in this particular situation, you've got two 66-foot legs. Notice that the radiation resistance is a little bit higher. That added capacitance, in spite of the fact that you're looking at a 30-foot vertical section, the feed line, it does tend to increase, but our capacitive reactance has gone down. So in this particular case, we've dropped the voltage to 2.4 kV at the base. For a variety of feed point resistances, we also have listed here a number that shows the amount of power required to achieve the maximum legal power, 5 watts EIRP. 32 watts at 10 ohms. As I mentioned, for the average station running 30 ohms of feed point resistance, you can usually get in with under 100 watts. For people with a lot more resistance, subsequently less efficiency, you're talking about a little bit more. But a person that takes attention to their loading losses, their ground losses, and their top loading can really get away with some pretty low levels of power to get on the air with. So, taking this one step further, we'll look at the 80-meter dipole, which has been improved by adding 2 parallel elements. In the process of doing this, you not only increase your bandwidth on 80 meters, so someone could come up with a means of switching the coaxes out or whatnot, relays, but they've also increased their bandwidth on 80 while decreasing once again their capacitive reactance. They need less coil to resonate it, and they've improved their radiation resistance and subsequently dropped the voltage at the base. The required power also drops pretty significantly. This is a really good way to improve reducing your loading requirements. Anytime you can reduce your loading requirements by reducing the capacitive reactance through the use of capacitive top loading, that's a very good thing. So a lot of people say, how do you find out how big a coil to make? Well, you're going to have to measure the capacitive reactance, model it, or calculate it by hand. And there are a number of approaches to that. If you are going to measure the capacitive reactance, let's say a dipole configured as a Marconi T, you're going to want to do that fed against a radial system because it will change with the ground losses. Modeling will give you some ideas about what it is. We typically use the perfect ground gain model whenever we are modeling this. So that does mean that they will be different when you go and apply this in the real world. The reason we use the perfect ground gain model whenever we're figuring our radiation resistance, when we're figuring these values, is that it keeps us out of trouble. You can't do any better than that. And so it keeps you under the theoretical, it really acts as a theoretical limit, keeps you under the maximum power levels and keeps your system legal. So once you have that value or calculation of capacitive reactance, we know that the absolute value of capacitive reactance is going to equal the absolute value of inductive reactance. The net difference is going to be 0. So in that one case of 1954 ohms of capacitive reactance, we need 1954 ohms of inductive reactance. That inductive reactance is found in the form of an inductor, of course. And we're going to go through the process of just basically plug and chug with the numbers, being careful with the units. Once you've got that value of inductance, you can plug that into a number of calculators to get the values that are available. And I think that it's actually more simple than most people really think. One of the things I like about the variometer approach is that if you're using a 5-gallon bucket like most people typically do in that regard, you can pretty much resonate anything from a 30-foot vertical on up with that, provided it has some top loading. So you've got a lot of flexibility using that approach. Matching the antennas, I like the L network approach, this being the loading coil. I have a shunt capacitor that it's actually a vacuum variable. It's motorized. It allows me to go anywhere in the band. It is a very high Q approach, and you will find yourself adjusting the capacitance on a fairly regular basis if you do move around. There also, okay, here we go. There also is the possibility of the hairpin match. In effect, a lot of guys take the variometer and they'll ground the bottom of that coil to affect their match. And in effect, that is an auto transformer, a hairpin match approach. That can also work very well. You really have to determine what your need possibly is. The final approach that I'll mention is the ferrite transformer approach to matching. Ferrite is a decent way to do it. This particular case, it utilizes the tapped coil to ground, and basically you're putting you're applying your power here to the transformer. You also have the capability of a galvanically isolated transformer. This is actually an incorrect drawing. These grounds are not common grounds. We like to keep our feed line isolated in this particular configuration because it minimizes common mode currents on the feed line. But in this particular case down here, this is NO3M's new approach to matching his 68-foot vertical. And I think he uses something like a 5 to 7 turns ratio to give him 25 ohms to 49, roughly 50 ohms of impedance transformation. There's a lot of information on the internet out there on the various approaches to transformers. So that's what I have as far as the process of building antennas, putting the vertical on, putting it together, getting it on the air. What I do want to spend a few moments before we take questions is I want to discuss a little bit about this idea of radiated power and really my thoughts on radiated power. Let me begin by saying that this idea of effective isotropic radiated power is really a challenging thing to get right. What we oftentimes find ourselves doing is exercising due diligence and doing what we can to make sure that we at least think we're in compliance or at least work that direction on paper, so that if anyone ever asks us what our situation is. In my particular case, I've taken a tremendous amount of data on my system. I've probably got 5 or 6 years of data, in some cases taken every day. So when someone comes to me and says, hey, I think you're running illegal power, I've got a lot of data that I can show them, calculations. I can show them that, hey, here are the measurements, and here is the information that's here, and I've got a pretty good idea about my particular system. And I would encourage other people that are trying to do this as well to utilize the same approach. It's not something. This is not a cut and dry process, okay? And you're not going to go take one measurement and that's going to be the measurement. It's probably going to change seasonally. It's probably going to change with the weather change. But the very first spreadsheet that I'm going to talk to you about is the one that allows us to accurately determine our radiation resistance. You can use models, you can use other ways. This is the way that I do it. And this is a spreadsheet that was developed by W0YSE Neil Clegg, based on the Laporte engineering text. Of course, Edwin Laporte was the chief engineer for RCA for many years, and he had some very unique yet very accurate approaches for making determinations of radiated power as well as radiation resistance. And in this particular case, for a 45-foot vertical, using 100 feet of top loading wire, so in other words, 2 50-foot wires or as a Marconi T, or maybe a 100-foot inverted L, we show up with a radiation resistance of 0.5378 ohms. And we're going to take that number, we're going to plug it into this secondary spreadsheet that I like to use. 45 feet is roughly 15 meters. Capacitance is going to be roughly 375 picofarad, which I'll confirm here in just a few moments. I've made a measurement of that system that says that I'm, I don't know, somewhere in the 22.5 ohm range. My particular system ranges between 16 ohms and 22.5 ohms at my station on a suburban lot. That's actually quite high. But because I do live in a suburban lot surrounded with houses and trees and other implements of real life, that does tend to push my loss resistance up just a bit. In this particular example, we see that 70 watts will bring us to 5 watts effective isotropic radiated power, which is and I've plugged in that value of 0.5378 for radiation resistance. I'll make sure that Mark has this spreadsheet as well as the other one available so that he can put it on your website. As you can see in this configuration, it's 1574 volts RMS and needing almost 300 microhenries of loading coil to resonate it. I'd highly encourage you, as you're developing your coils, build them large, figure them large, because it's easier to cut wire off than it is to add wire later. In closing, I want to show you one additional site. 472kilohertz.org has a nifty little calculator that you can play with to make some of these calculations. Now, the caveat is that your antenna is less than 95 meters total length. That's both vertical height and horizontal height, or horizontal length, I should say. So in this particular case, if we select let's say we select the Marconi T, 15 meters, total length, we'll say 33 meters for the top loading wire, and we go, and we say, let's say, we'll say average loss. Then you're going to find here the radiation resistance that it figures is pretty close. It's a little bit higher than what was figured during the other estimate. We're also pretty close on the required antenna, or the noted antenna capacitance, but we're also going to require a little bit higher antenna inductance to be able to accomplish that. In this particular case, it's telling us that for 5 watts EIRP, you need about 60 watts of power out of the amplifier to accomplish 5 watts effective isotropic radiated power. So you can use that tool to also check yourself. What you should take away from this is that none of this is black and white. Okay, it'll change regularly, and depending on the calculation and the approach you use, it'll be different. A lot of times people will say, well, shouldn't I just use the field strength approach? But trying to take field strength readings, forget about the fact that the equipment itself is hard to come by, and building your own creates all sorts of challenges, primarily because of the calibration issue. But trying to take field strength measurements of a suburban antenna is really bordering on impossible. If you had 50 acres of flat open space, you know, maybe you could make a proof similar to what you might for an AM station, but it's very difficult for suburban antennas. So references: 472kilohertz.org, antennas by N6LF. This is Rudy Severin's page. He has an entire book that he's put together of PDF files. Of course, my page here, njdtechnologies.net. I've got all sorts of information: Hall of Flame, links page, instructional information. Hall of Flame. Let me go ahead and pull that up just to show you what that's all about. While that's loading, I'll go ahead and talk about the next one is John Molner's page, wg2xka.wordpress.com. This is WA3ETD site. He's got information on building the variometer. And one of the resources that I relied on heavily today is Eric Chansky, NO3M's antenna presentation that he gave at DATE. And he's got a tremendous number of models in here that he didn't really even get to scratch the surface with at date because there's so much information and there's so little time available. I highly recommend you download his presentation here and go through it. It's also got some information in the last half talking about receive antennas. Now, so let's talk about the Hall of Flame. This is Roger Cross antenna. It looks like a power line that's down. And basically set an antenna on fire in the process. Lawrence KL5NJD, this is with 55 amps of RF current running through his 137 kilohertz loop. And this is the bolt that evidently had some flaws in it that ultimately failed. I mentioned Larry Molitor's coil that was located high up in the antenna. Well, this is his coil after he took it down. And I trust Larry's judgment on this. He's quite possibly the most astute engineer that I've ever met. And so if he says that this is the wrong way to do it, this is the wrong way to do it. This is actually my personal oops at my station. I had some plastic tubing that was covering some wires, and one morning started a fire in my ATU that fortunately the power supplies realized the overcurrent condition and shut the system down before it got really bad. This is Neil Clagg's at his station up in Vancouver, Washington. He had a jump across an insulator to ground. PVC is not necessarily a very good choice of insulators. It will carbon track. If you're going to use whatever you use for an insulator, I recommend you going out and power washing it probably once a month to keep residue from rain from falling on it. Wood's not a very good insulator at these frequencies either, so be real careful. That was John Molner's. This one's pretty dramatic. This is Ralph W5JGV. He used some PVC to do some standoff for his feeding of his antenna, and things didn't go so well. Here you see some more fire damage, and Merv K9FD out on Molokai in Hawaii he used PVC in his system from this old broadcast site. Ben, I mentioned Ben N1VF. Well, he set a tree on fire and from his suburban San Francisco location, and he's had a lot of us have lived vicariously through him as pyros. It's been a really amazing thing to watch him burn things up. And Paul W0RW, he burned up he had a battery explode in the back of one of his transceivers sometime back. Jan LA3EQ had a wire that somehow became disconnected and started a fire on the side of his building. So this can get real serious whenever you start talking about structures that can't catch fire. So be real careful out there. There's a lot of opportunity to hurt yourself and someone else if you're not. That's all I got. I'm happy to take questions. Thank you very much.
Yahoo! We have some weird things in the air, John. Let's go ahead. Peter.
Can you hear me okay, John?
I sure can.
Okay. On the Hall of Flame there, the pictures are very dramatic. The most important question is left unanswered. Did they complete the QSOs?
Of course. Of course they did. Yeah.
That's important.
Just got to push through it.
That's right. Thank you.
Any other questions? I got one from Ken. You might know that guy.
Hey, John,
Okay.
Ken, K5DNL. Thanks for the outstanding presentation.
Yes.
I
Yes.
appreciate it.
I agree.
It's been fun.
We will be calling you again for July 27th for Ham Holiday in Oklahoma City to do this one more time.
Okay.
So you're on. You're on
Very good. Well, let me say this here, and I've actually written about this in my I guess it's my June. I guess it was my June CQ article. Not June, October CQ article. I would encourage you guys to give serious thought about setting up a station at your field day site, and let's pass some traffic on the air. Let's do this. I would, I would encourage you to do that. I'm actually pushing a number of operators, a number of groups in the local area to do that. I got a bit of a late start this year. I'd love to be able to do it. I'm kind of trying to nudge the ARRL in that direction. It's been a bit of an uphill battle, but just because they don't give points for it necessarily, there is some value there. So I would encourage you guys to work towards that. Send notification for your field day site, and let's get something on the air field day.
I think that's a great idea. I have one question in regards to that. Let's say that I've already put my my UTC stuff in. If I put a second one in with my same call sign at a new location, does that invalidate my first one?
Not a problem at all. In fact, I've registered about 50 locations around my area. A lot of those are parks. I've even registered a park bench out at the local state park that I like to operate from time to time. HF, that at some point I'm going to operate fixed portable from that location. I've really just gone around and registered locations that, I say registered is really the wrong word, notified them of my intent to operate from a number of locations, many of which I've not even operated from. But that's really the way you get around this prohibition on portable operating, is just go registering all of the sites that are possible, and pretty soon, if you decide to operate there, it'll be available. If you're somewhat worried about using your personal club sign, you can certainly use your club's call sign. That's not a problem either.
Second part is, we're on an airport, and what do you see this low frequency stuff doing to airport operations? Are we going to get in trouble there?
Not at all. The main issue is PLC, which there is no active PLC above 300 kilohertz in the lower 48.
Yep.
So it's not a problem there. In terms of navigational beacons, you more than likely, you may or may not have a navigational beacon at medium wave or long wave at your local airport. Most of them are transitioning to other technologies as their old NDBs fail. But you're not going to create a problem for those. Again, making sure that you're using very good quality filtered output on your amplifiers. You know, as I mentioned earlier about using the transceivers that are wide-banded, you know, you want to use good quality low-pass filters because you want to avoid any harmonics that might impact, whether it be the broadcast service up above, or whether it be the navigational beacons that are below. And I will mention that there are, the second harmonic and the third harmonic fall within the AM broadcast band, so that filtering is very important. So to getting back to your question specifically, as long as you're using filter power and good quality system, you shouldn't have any problem with those navigational beacons.
Super. Thank you very, very, very much for your time. Awesome presentation, sir.
Thank you very much. I'll put points complete and some additional information here shortly. And if you have any questions, don't hesitate to contact me. I think it's really important. You know, the art of Elmering is really lost, and so I think it's important to contact me, contact Ken, and let those of us who are on the air help you get through it. There's no reason to struggle through this. A lot of people get frustrated and give up because of some very simple things that we can correct. Thank you again.
You're the man. Thank you, sir. See you some other day.
All right.